decimal to 1 conversion, decimal to binary, octal, hexadecimal. Now let's try to understand how to convert decimal number systems to binary, octal and hexadecimal number systems. Now for example, we have a number 90, a 10. We need to write base also. Suppose in our example 90 is given. This is in decimal number systems. Then how to convert it into binary number systems? The way to convert this decimal number system is into binary number systems. We need to divide. What does binary means? Binary means 2. We need to divide 90 by 2 repeatedly. 90 by 2, what is 45, and 45 by 2 again, and so on, until we reach to the positions where remainder becomes less than 0, less than 2. That means let's divide 90 by 2. What will be 45? 45 to the 90. And what will be the remainder? Remainder become 0. Now 2. 22. 22 to the 44. That means remainder become 1. We need to do in this way. 2. 11 to the 22. Become 0. 2. 5 to the 10. Remainder 1. 2. 2 to the 4. Remainder become 1. 2. 1 to the 2. Remainder become 0. Now we obtain this result, and we need to organize this remainder from bottom to up. Now what would be its result? Now let's see. What is first digit is 1, 0, 1, 1, 0, 1, 0. This is the binary number equivalent of this 90 decimal number systems. We use this method to obtain the binary equivalent from the decimal number systems. Now we divide the number by 2, and we now for example 90 divided by 2, we obtain 45, its remainder is 0, and so on up to the number up to until we don't get the number less than 2. Now this is the binary equivalent of the 90. For example, if this decimal number contains the fractional number, what is the fractional number? Fractional number is those number which have a quantity less than 1. That means, for example, in our case 90.25. Now how to get the binary equivalent of this number? Now yes, we need to separate integer part and fractional part. This number contains the integer part 90, and the number after this decimal point is called the fractional number. Integer number and fractional number. Now we obtain the equivalent binary number of the 90. Now we need to find the equivalent binary of this 25. The procedure to obtain the binary equivalent of this point 25 is, now let's see, what's the procedure to obtain the binary equivalent of this 25. We need to make a table. For example, 0.25. We need to multiply it by 2. To obtain the binary equivalent, we multiply it by 2. What would be its output? 0.50. and we need to separate the integer parts. What would be the integer parts? Integer part only contain 0. Now what the fraction parts remains? 0.50. Again we multiply this number by 2 and we'll get 1.0. What would be its integer part? 1. Then 0. Fraction part is 0. Now if we get the fractional part 0 or repeated number, then we need to stop this iterations. Now for the fractional number, we need to arrange this number in this integers number in the top down way. That means we need to write what would be the equivalent binary of 0.25 dot 0.25 10 equal to 0.01. This is way 0.25 equal to 0.01 binary. We use base 2 to represent this number is binary. Now this is the equivalent of the 90 and dot 01 is the equivalent of 0.25. That means 10111010.01 is the binary equivalent of the 90.25 decimals. Now similarly, to convert this into octal number systems, we use the same method similar to the binary. We need calculator to perform this. Now 90. To get the octal equivalent of this decimal number systems, instead of dividing by 2, we need to divide it by 8. Now 90 divided by 8, 11. 11 is 88. 88, 89, 80, 90. That means reminders become 2. And again it need to divide by 8. What is 1 is 8, 9, 10, 11, 3. Now we need to write this from organize this from bottom to top. That means what would be the equivalent of 90 in the octal number systems? 132. 132. And how to write? 8. We need to write 8. Now we need to again convert 0.25 into octal number systems. Similarly we'll do 0.25. 0.25. We need to multiply it by 8. Zero point 25 into 8, 2. 2.0. That means we need to separate 2 and integer part here and fractional part here 0. 0 is this. That means we need to write 2. What would be the extra output? 0.2 octal. This is the 132.2 is the equivalent octal number systems of 90.25 in decimal number systems. This is the decimal number system and its equivalent octal number system is 132.2. Similarly, to obtain the hexadecimal equivalent of this number, what would you do with the now? Again, we need to separate 90 and 25. That means we need to separate integer part and fractional part. We need to find out the equivalent hexadecimals of the integer part and equivalent hexadecimal of this fractional part separately. So that first of all, let's first find the equivalent hexadecimal of this 90. 90. Let's divide it by 16. To get the hexadecimal equivalent, we need to divide this decimal number systems by 16. 5 ja 80. And what would be the remainder? 10. 10 means in the hexadecimal system, 10 means A. Why here A? If we divide 90 by 16, then quotient become 5 and remainder become A. A means 10. That means we obtained 5. 5 is the less than 16, so that we need to stop the iterations. And we need to organize from bottom to top for the integer part. So that what will be the equivalent of 95A? Now 5 is the equivalent hexadecimal of the 90. And how to obtain the hexadecimal equivalent of the 0.25? Now similarly 0.25 and into 16 will do 16. Now 0.25 into 16, 4. We obtain 4. 4.0. We need to write integer part here 4. That means 0. We obtain 0, so that we don't need to go further. We just need to write 4 dot 4. 16. Now 90.25 is our decimal number and its binary equivalent is 10111010.01 and its octal equivalent is 132.2 and its hexadecimal equivalent is 58.4. In this way, we can find the equivalent binary octal and hexadecimal of the decimal number systems. Now we will learn how to convert binary number systems to other number systems. Now let's see an example. Now let's see an example how to convert binary number system to decimal, octal and hexadecimal number systems. Before doing these operations, we need to understand, first of all, we need to understand the positions. Suppose 84. 84 is a number. This is the integer number. Integer number means that do not contain the fractional part. Now this is the integer number. Here, for this integer number, we can append any number of 0 on the left hand side. Not only for decimal number systems, for any other number system, for example binary, octal and hexadecimal number systems also, we can append any number 0 on to the left hand side. This do not alter the value of 84. We need to understand this. But for 0.84, now how to write this? We can append This is the fractional number because this contains the 0 here. 0.84. We can also write this in this way. 0.84. In this number systems, we can append any number of 0 to the right hand side of this fractional number. Okay, this do not change its value. If we add any number of 0 to the right hand side of this the given number, then this new found number is still represent the same quantity as previously represented by this number. So that we need to understand for the integer number we can append any number of 0 to the left hand side. For the fractional number we can append any number of 0 to the right hand side. Now we'll see where it applies later while converting this number to the other number systems. Now binary number to decimal number system. How to obtain the decimal equivalent of the binary number system? Suppose 1101. This is the binary number systems. In our case, 1101 is the binary number system. And what would be its decimal equivalent? What would be its octal equivalent? And what would be its hexadecimal equivalent? We'll understand by doing this exercise. Now let's see. First of all, we were trying to convert this number system into the decimal equivalent. Now to convert any number into decimal number systems, we need to write in this way. 1. What is the symbol given here? 1. And for each symbols we need to write into 2 plus into 2. Why 2? 2 is the base. Plus 1 into 2 plus 0 into 2 plus 1 into 2. Now look at here. We need to write in this way. For each symbol we write into 2 plus. For this symbol 1 into 2 plus 1 into 2 plus 0 into 2 plus 1 into 2 plus. Now we need to see its position because this is the positional number system. Position determines its weight, so that we need to see its position. That means 0. Its position is 0. Its position is 1. Its position is 2. Its position is 3. In the same way, we need to write the power of 2 at the position of these symbols. Now, what is the power of 2? 0, because position of 1 is 0. Positions of 0 in this number is 1, so that we need to write power of 2 1, power of 2 3 in this way. We need to write in this way. Now what is the cube of 2? What is the cube of 3? 2. What is the 2 to the power 3? 8 plus what is power 2 to the power 2? 4 plus 0 into any number gives 0 plus 1 into 2 to the power 0. 2 to the power 0 gives 1. Any number to the power 0 gives 1. That means 2 to the power is also 1. 1 into 1, 1. That means 8 for 12 and 1, 13. This gives 13. And this is the decimal equivalent. That means 13 is the decimal equivalent of 1101. Now, suppose this number also contains the fractional part. Binary number could also contain the fractional part. Now, let's see an example. Dot 1 1 1 0. Now let's see this is an example. This is the binary number and we need to find out its decimal equivalent. 13 dot. This is the integer part. Now it contains the fractional part also. We need to count from positions from here. Now what is its position? 0. For the left hand side contain the integer. For integer part we do the same procedures. The first digits is at position 0, second digit is at 1, third is at 2, fourth is at 3 positions. Now, how to count this fractional number, fractional symbols? We need to take this dot sign as a reference points and begin to count. Now 0. The first positions of the first symbol is -1, -2, -3, -4, -5. Similarly, in this way, we need to write all this fractional number or integer number into 2 to the power its positions. Now, let's see. 1. What is this? Is the 1 into 2 plus 1 into 2 for this 0, 0 into 2 for this 1, 1 into 2 plus regardless of the dot, we don't regard this, just write plus 1, 1 into 2 plus 1 into 2 plus 1 into 2 plus 0 into 2 plus 1 into 2. Now, look at it. 1 into its position is 3. 1 into its position is 2. 0 into its position is 1. 1 into its position is 0. Now, 1 into 2 to the power -1, -2, -3, -4, -5, -5. Now, we use calculator to calculate this. This will give 1, 3 dots something. We need calculator to perform these calculations. And this is the way we obtain the decimal equivalent of the binary number. Now, how to convert this binary number into octal number systems? Let's see how to do this. These procedures are quite easy in comparison to the conversions to the decimals. Now, how to convert this to the octal number system? Suppose this is the binary number system, and how to convert this number system into the octal number systems? Now, to convert binary number system into octal number systems, we need to make the group of the 3 digit. This is the simple procedure. Group of 3 digit. Now look at here. We need to take dot as a reference point. And we begin from this dot for both integer and both fractional. For integer, we need to make group of 3 digit. That means 101. First group is 101. And second group would be 1. It contains only 1 digit. We need 3 digit to make a group, so that we can, for integer number, this is the integer number, we can append any number of 0 to the left hand side. That means 2 groups are formed here. For the fractional number also, we need to begin formation of the group from dot to the right hand side. Now, first 3 digits are 1, 1, 1. 1, 1, 1. This is one group. And second contain 0, 1. There is still 1 digit is remain. That means it contains only 2 digits. We need to make 3 digits, so that for the fractional number, we can append any number of 0 to the right hand side. That means this will become again the group of 3. Now, we need a conversion table. We can count the decimal number systems. For example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 in this way. But how to count the binary number? To count a binary number, let's see here. 1, 0. 0 is written by 0, 0, 0. 1 is written by 0, 0, 1. 2 is represented by 0, 1, 0. 3 is represented by 0, 1, 1. 4 is represented by 1, 0, 0. 5 is represented by 1, 0, 1. 6 is represented by 1, 1, 0. 7 is represented by 1, 1, 1. Now, this is the conversion table. How we count in binary number system? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. This is the simple conversion table. We'll write another conversion table also using the 4 digits. This is the 3-digit representation. 3 digit is sufficient to convert from binary to octal. Now look at here. 001. What is 001? Its equivalent is 1. That means 1. 101. 101. Its equivalent is 5. Dot. Dot. 111. 111 means 7. 010. 010 means 2. That means this is the octal equivalent. 15.72 is the octal equivalent of 1101.111011. This is the octal equivalent of this number, this binary number. Now, before converting binary number to the hexadecimal number system, we need to understand the conversion table in the hexadecimal number systems. Now, hexadecimal, we wrote group of 3 digits to convert the equivalent octal number. Now, to make the equivalent hexadecimal number systems from binary number systems, we need to make the group of 4 digit. Instead of 3 digit, we need to make group of 4 digit. That means, now look at here, 4 digit. This is a simple conversion table from octal to binary. Now we can append 0 here. Okay, for any number, we can append any number of 0 to the left hand side for integer number. Now 8. What does it mean? 8 means 1 0 0 0. 9 1 0 0 1. 10 1 0 1 0. 11 in the context of decimal number systems, but B in hexadecimal number systems. In hexadecimal number system, 10 means A. 11 means 1 0 1 1. C means 12. 12 means 1 1 0 0. D means 13. 13 means 1 1 0 1. E means 14. 14 means 1 1 1 0. F means 15. 15 means 1 1 1 1. Now this is the simple conversion table. We need to use this conversion table while converting from binary to octal and hexadecimal. We already obtained the octal equivalent of this number. Now we need to obtain the hexadecimal equivalent of this binary number. Now look at here. This binary number contains the both integer part and fractional part, and we need to convert it into hexadecimal number system. To convert into the hexadecimal number systems, we need to make group of 4 digit. That means it contains the 4 digit. Is alright? Okay. 1 1 0 1. If it could not contain the 4 digit, then we could add sufficient number of required number of 0 to the left hand side, because this is the integer number, and we need to formations of the group from by taking the reference of this dot point. Now we made the group of these 4 digits, and we need to make group of 4 digits for the fractional number also, beginning from this dot to the right. Now look at it. 1 2 3 4. Let's first take 4 digits. That is 1 1 1 0. We made a 1 group. Now the second number only contains 1, but we need to make a group of 4 digits. That means we can add sufficient number of 0 to the right hand side for the fractional number. That means we obtain this number. Now what does 1 1 0 1 means in hexadecimal number system? 1 1 0 1. That means D dot 1. What does 1 1 1 0? 1 1 1 0 means E, and 1 8. This is the hexadecimal equivalent. Now we obtain the decimal, octal and hexadecimal equivalent of the binary number. We apply the same procedure to obtain to convert the binary number into any other number systems.